quick recap then before we go into the demonstration itself. So what I've described so far are the API routines that we have as part of ImperasDV. We have the interface, which we call RVVI, which is used to capture information being generated within the RTL and test bench and pass it on to the ImperasDV environment. And then we have the semantics of the operation, which is there's a prologue phase which sets up the environment. We have an execution and comparison phase whilst we're executing the code. And then we have the epilogue phase, which is where we would write out any statistics. So now let's show this in action. And what we're going to do here, I'm just going to flip across to my demonstration area. The first thing I'm going to show, I've got this all scripted up, by the way, because it makes it a lot easier to actually run things. I'm going to show running one of the compliance tests on the IBEX core RTL and being compared and controlled within the ImperasDV environment. And this is the add test that we're going to run here. So let's just run that. I'm actually running this under a commercial Verilog simulator. So we go through the compilation elaboration phase and then we go through the execution phase. So here's the interesting part here. There's not a lot to show because, of course, this is working perfectly fine. And in fact, all that happens is when we execute that program is that we get a summary telling us that we've performed a number of assignments or sets, which is where the API has the client watching the RVVI interface has controlled the API to set information in the ImperasDV environment, and then it's done a number of comparisons. So here we see we've had on the PC 200 sets, 200 compares. The instruction bit pattern, when we perform a fetch, we've got 200 sets, 200 compares, and on the GPRs, then we have 200 sets and 6,400 comparisons. The reason why we have 6,400 comparisons here is because, of course, there are 32 GPRs. And not only do we check for GPRs that get set, we also look for side effects for ones that we ensure have not been set. So ultimately running this, it tells us we have 6,800 comparisons and we've had no difference. So I sometimes liken this environment to what we have here as to having a very smart assertion checker in your code. You know that in general you expect it to be silent, but when something goes wrong you want it to raise a flag and tell you that there's a problem. And so this is kind of like the silent scenario that we're watching here, that it's running in the background, it's doing lots and lots of checking, but it has nothing to tell us right now because there are no differences inside of this environment. So what we're going to do next is we're going to introduce a bug into the RTL. And so where I'm going to do this is in the ALU. You'll see here in this ALU, we put in a hash define or a tick define in terms of Verilog speak for something to corrupt the behavior of the ALU add in the ALU sub function. And what we can do is we can enable or disable this through our command line to exclude this bit of the code. Now, of course, the example I have here is running the ALU compliance test. So if I introduce a corruption here, I'm pretty hopeful that the compliance test should find this. So let's just have a look at the script that we're going to run here. So as I mentioned, you know, we've got this tick define that's going to be enabled. And if I now run this, let's see what happens at this point. So again, we go through the elaboration phase. I've actually got this configured at the moment to tolerate 5 miscompares, and this is programmatic. We can say how many we want it to absorb before it goes through to a bailout condition. And what it tells us here is that this program counter where we've executed an instruction, which is D8, we've got a miscompare. It's telling us that the device under test told us that the value of the X5 register was 0 and the value of the X5 register in our reference model under ImperasDV was D8. Because we've got the miscompare throttle to 5, then the program does actually continue executing, but of course this is continually reported. And then what we see is a further miscompare at this point where we also have a miscompare in X10. Now, the first thing I would mention about this is that unfortunately we don't really have a lot of information here regarding the flow of execution that led up to this point where we saw the difference. And this is now where we start to get into the details of how we extract more information whenever we get problems with the state comparison between the RTL and the DUT, the RTL DUT and the ImperasDV environment. So the first thing I'm going to do here is to turn on some additional tracing. Again, it's actually scripted up here. And what I'm going to do is I'm going to turn on the tracing of the reference environment. And I'm going to, and if you recall earlier, I said that there are a number of things that we can control at runtime. There's a number of things we can control at compile time of the processor reference that we're using. So here's an example of where we're doing some controlling of the runtime side of things. So we're telling it to do some additional tracing, trace changed registers, give us an instruction count, tell us about modes if it's switching. It just so happens in this one actually it only runs in machine mode, but if we had a more complex core then it would tell us about mode switches as well. So let's run this again. So it's still got the RTL fault in there. We're going to execute and see what additional tracing we get out. So you'll see here, this is the tracing now coming from ImperasDV, and it tells us at this point here we're executing an AUIPC instruction, and an AUIPC basically says add unsigned immediate to the program counter, and the unsigned immediate is 0. Therefore, we're just going to write the program counter into register X5. And yep, great, it tells us we've got D8 in the register X5. Unfortunately, the RTL, the RTL tells us that it has 0, and this is why we had that difference at that point. And so if we continue executing, remember I said that X10 also has a fault in it, and so here we see an X10 failure because at this point here we've done an add immediate targeting X10, and again the RTL is saying that it has the value 0 in X10. Now let's turn on some further tracing. So what I also want to do is turn on some tracing from the RVVI interface. Remember I said that there are clients that we attach onto the RVVI. One of them is controlling the ImperasDV API calls. And we have another one which we call the VLG to log, which is watching the transactions and can log those transactions out based upon what is occurring on that RVVI interface. So let's run that now. So now we're going to have some logging of the interface itself and of our reference model. So this is actually more interesting now. So what do we get? So if I start at the beginning and then we can see the flow here. The first thing is that, so this is a message that's coming out of the logging of the RVVI interface. It tells us that an instruction was retired on heart 0. Its order was 1, so it's the first instruction, and it tells us the address of that instruction, it tells us the bit pattern of that instruction, and it tells us the disassembly of that instruction. And it also tells us that there were no register updates associated with that instruction, which is what we would expect because there is no change at that point. The next instruction to be executed is a CSR read into the from the heart ID into X10, and so it reports that we've got a change on X10. It just so happens that that's a write, and I think it's and so it's writing in the value 0. And when we do the same operation on on our model, it compares because the default value is 0 at that point. Now, where we get the difference is more interesting. So if we extend out the difference here. So we see that the RVVI is reporting that it's retired an instruction, which is our AUIPC, but it's telling us that register X5 has the value 0, whereas the reference model has told us that it should have the value D8, and this is where we get our difference. So now we know exactly why we have a divergence between our design and the test, for the RTL for this, and we have a different value calculated in the reference environment. Now there should be no surprise here, right? Because we've introduced a bug into the RTL. So of course the next thing we would want to do at this point is to take that bug away. So what I'm going to do here, let's have a look at the next script. In fact, no, I'm not going to run that right now. What I'm going to do first of all is I'm going to modify our existing script, and I'm going to turn the error off. And I just want to show that now what we should get is an execution to the end with no differences, because there we go, that's perfect. So now we see, as we had before, except we've still got the tracing turned on. That's the important thing to note here. So when we ran the first example, all we got was the summary at the end, whereas now, in addition to the summary at the end, because we've got the tracing of both the RVVI interface and the tracing of the reference implementation, then we've got a lot more information at this point here. Of course, sometimes the problems that we have to investigate are far more complex than this, and can't simply be resolved by looking at traces, and we have to go into a mode where we do some interactive debug. And so what I want to move on to now is just showing how these tools and these technologies can help even during interactive debug. The first thing I'm going to show is adding some debug from the perspective of the a system Verilog domain. So again, I've got a script set up here. So what this is going to do is it's going to run up a Verilog waveform viewer, and we can take a look at the content of the RVVI interface that is being driven from our model, from the RTL model, that is. I've already pre-selected some of the signals here to make this a bit quicker as far as demonstration is concerned. But the important thing to note is I've gone back to the point where we've got the bug inserted in the RTL, and so we see after 5 miscompares that we're going to perform a finish of the simulation at this point. And this is a cut down set of signals within the interface. It's really the only ones we're interested in looking at, because as I mentioned before, the IBEX core only supports GPR registers. There's no vectors or anything like that in here. But what we can do is we can push down and look at a lot of information and determine what's going on. So if I look at, first of all, the instructions themselves, here I see the instruction bit patterns that are being applied to the bus to the interface as we're executing our code. I can see the program counter. Let's move that up there. I can see the program counter value as well for those instructions that are being executed. So we know here that the first fetch occurs at address 80 on the IBEX core. And then in addition to that, we can see the transitions of, for example, the order, which is effectively the count. That should be really represented as let's change the radix. That should really be a decimal, so let's change that to decimal. So here we see the instructions in terms of their order definition as part of the RVVI interface. And then we see the individual registers on our heart 0 for issue 0 of all of the GPRs 0 through to 31. But as we've already discussed, that there are no changes to these registers as we're executing, because of the problem we have already investigated here. Because of the environment we're working in here, we have access to a greater set of tools. We don't have access purely just to the system Verilog tools, because we also have the tools that come from the ImperasDV environment, and so we have interactive software debuggers on that side. And so what I can show here is running the interactive software debugger alternately to, or actually complementary to, running a waveform debugger as well. So we'll do the same thing here. Let's run up, we'll actually run up both. We can do this, and let's start the execution of the system Verilog simulation environment. If you recall, I mentioned earlier that we kind of act as a slave to system Verilog, and therefore we have to start the system Verilog simulation running. But once it's executing, we can take over control within our debug environment here. So I can step through the code. I can view registers. So if I open up my registers here, if I start stepping through the code, we can see that these will eventually get updated. There we go. We see an update of a register there. Interestingly, if I go back to my console here, it's going to report to me, same as before, telling me that we've got miscompares with the RTL at this point, because the add function is not working inside of the RTL. But the nice thing about this environment here is that you have complete visibility of everything as far as the reference is concerned. So you have the software view of the registers as they appear on the stack, assuming that they're conforming to some kind of ABI. And you also have visibility of the registers as they would appear in their physical hardware form in this window here as well. So if I was running a more complex program here, it just so happens that the compliance tests are written in assembler, but if I was running a high-level C program and I had a deeply nested stack, as I moved up and down the stack here, what you would notice is that the software registers, of course, would change context and value based upon where they were in that software stack. Whereas, of course, the hardware registers would remain the same. So you're able to contextualize these two against each other. And we have, a full software debugger here that allows us to go and look at the code that's executing. We can look at the source code if there was, source code rather than assembler in here. And we can also go and look at all of the internals, including, not only the core registers, but things like the machine control state registers and recording information such as internally held state for what mode we're operating in or what the last exception was that occurred. The last part of the demonstration I want to show here is some of the built-in coverage capabilities we have with the ImperasDV product. The first thing I'm going to do is I'm going to rerun the first example. If you recall, this was simply running the compliance test for the add instruction. So let's just set that one off again. And in the background, I'm actually generating some coverage, as you can see here. I haven't highlighted this before, but we're capturing coverage as we run this. And if we look at the coverage report for running that test, what we see is this is broken down into individual tests and then cross coverage between source and destination registers and an accumulation at the bottom, which I'll show you. So if we look here, so we've got some cross coverage of RS1 and RS2 input operands, and we've got some coverage for the individual destination and source registers. So this particular test that was written by the compliance group has pretty much targeted all of the combinations. As you can see, they're all hitting 100%. But more interestingly, if we go down this file now, we'll notice that we start to hit some zeros. And this is because these instructions are not being targeted by this test. This is a specific test to exercise the add instruction in the I extension of the subset. And we get a summary at the bottom telling us that we've exercised and counted so many instructions, and tells us how many unique instructions and how many coverage points we've actually hit. Now what I can do is I've actually got a number of tests here. I think there are 5 tests, and I can run all of those tests. So let me do that. I've got a script here that's going to run all 5 tests. Where is that? Okay, there we go. And this is going to generate coverage reports for each individual test as it executes. But more interestingly, what it's going to do is it's going to also collate all of those and aggregate them into a single report, and we can extract that information and take a look. So we see here for this last test that ran, which was I'm not sure which one it was actually, but importantly here we see the 5 tests that we've aggregated. And this is the add, the and, branch if less than, load word, store word. And you can see here we've hit this many coverage points, so 503 out of 2,540 coverage points. In fact, let's do this, if I grep for this description here in all of the coverage files, excellent. That's what I would hope to see. So we can see that each individual test has a smaller amount of coverage than the overall amalgamation of those. So as we can see here, the add and the and are producing less than 10%, just slightly less than 10%, and the others are 7 and 6%. But when they're added together in this collated report here, then we see that we're hitting 500 of the coverage points. And obviously, as we add more tests into this set of tests, then when we generate the collated report, we'd start to see that our coverage improves overall. Hopefully this has given a good introduction into the work we've been doing with the ImperasDV capabilities for design verification of RTL RISC-V based processors. What I'll do now is I'll pass back to Simon, and any questions we can also address later on. Thanks a lot.